I did want to mention to the comment about spur dikes, I'm actually going to be talking about spur dikes here a little bit in the talk, but it's not specifically about modeling the detailed flow field around spur dikes, more so on how they affect a bridge downstream, and really how kind of the importance of that type of roughness on the bridge hydraulics that a lot of us really focus on. So I'm going to start out with a little project background just to provide some context on the analysis. So we were doing a project for Union Pacific Railroad. That's a replacement of their Mississippi River Bridge at Clinton, Iowa. So you can see the existing bridge there. It's I think it's about 400 feet long. It's a movable span, so it pivots there in the center of the bridge. The navigation channel is on the left side of the screen. You can see a large dolphin and a guide wall there to protect the pivot pier. And so they're looking to replace this mainly for maintenance and just risk of downtime and operation costs, more so than hydraulics. So this is what the proposed bridge will likely look like. This is an early rendering, but it's going to have about a 400-foot truss span over the navigation channel and about 65-foot clear over the normal pool. So the objectives of our hydraulic analysis were primarily to support floodplain permitting and Section 408 authorization for the Corps. The Iowa DNR will actually review a 2D model for no rise, and the Corps wanted to see the 2D model for the Section 408. So to do that, we had to establish an existing condition. We had an ultimate condition model, and then we also had to model temporary conditions because this project spans more than one construction season. They also use the results to inform the foundation design, so the scour analysis. This is an overview of the model extent. So the upstream side of the model is at the upstream boundaries at Lock and Dam 13, and the model length is about 6.5 miles. You can see the wing dams shown there in orange, and the federal levees there in blue. So to get to kind of transitioning to what I'm mainly talking about today is, so if we're interested in bridge hydraulics, what's the influence of wing dams? In this case, most of them were upstream of the bridge that we were interested in. What's the best approach to model those structures? And what's the effect of some other model inputs on the solution? And ultimately getting to the question of how's the modeling budget best spent? We had a lot of, it's a fairly large model extent. We had some bathymetry data from the Corps. They had a lot of single beam data. And we collected some multi-beam for the project. And, we had to incorporate levees. And so it's, how important is it to capture these wing dams on our actual solution? So, what can influence the solution? A lot of people, are doing 2D modeling now. These are the things we're looking at, the mesh, topography, bathymetry, your roughness, boundary conditions, all the way at the fundamental level, at the numerical scheme, and any 1D elements you incorporate. So when I talk about the wing dams in the Mississippi, what do those actually look like? So what we're looking at here is a composite DEM that includes LiDAR data in the overbanks and multi-beam data in the vicinity of the bridge, and single beam data upstream of that. So on the right side of the screen, there we have a couple sections cut. One's through the crest of the wing dam, and the other is just downstream of that. And then I also have, kind of in the direction of flow there, I cut a cross section. You can see it's about 10 feet tall, and it got a top width of about 20 feet in the direction of flow. So this is just to overall have an idea of what the scale of these features are. So the heavy brown line is the center line of the wing dam, and then the dashed brown line is downstream of that. So again, you can see it's about 10 feet tall, and we're showing the 2, 10, and 100-year water surface elevations. So you can see the 100-year is, the depth of flow compared to the height of the wing dam is about 3. It's closer to 2 for the 2-year event. And this is also, keep in mind, this is just looking at about half of the total floodplain, looking at the main channel. There's also a secondary channel in this area. So I went through and looked at, ultimately ends up being a sensitivity analysis. So I looked at several different mesh geometries. I looked at the effect of adding weirs as a 1D element. And I actually used 2Flow FV for a lot of the modeling because that's what we had chosen for the project. It's similar to SRH 2D in a lot of ways in that it's a finite volume model. They can actually use the exact same mesh. But we also looked at some runs with SRH 2D as well. So I looked at a variety of flow rates there, 44,000 CFS, which is a low flow, and then 2, 50, 100, and 500-year flows, and looked at how these different mesh geometries at different flow rates, how that affects the results. So flow distribution in a couple areas, and water surface profiles throughout the pool, and the velocity field. So when I talk about a coarse and detailed mesh, this is a representation of that. The overall mesh element sizes on the detailed mesh, I did about twice as much resolution in the area of the wing dams, which ultimately, if you were really going to evaluate the hydraulics in the vicinity of the wing dam, you would want to do more resolution than that. The coarse mesh is just kind of meshing up the channel as you typically would, and any modeling of the elevations in the wing dam were really incidental to just what the mesh picked up. So when we look at what that actually means for one of the areas of the mesh, it looks pretty washed out here, unfortunately, but on the left there is the coarse mesh. So this is actually in the area of a closing dam downstream of the bridge. So on the picture on the left there, the coarse mesh, you can see, probably have about 10 elements through this section that was cut. And in the right, we have probably 4 elements across the crest of the closing dam. And so you would think that would be quite a bit better representation in the mesh element elevations. But if we look at the cross section there on the bottom of the screen, you can see that actually the elevations line up pretty well. And so the detailed mesh on the right is blue on the bottom. And so you can see it picks up some higher peaks there along the closing dam. But the other thing to keep in mind is that, from what I understand, when you see these elevations in SMS, you're seeing node elevations and resulting interpolation between those elevations. And then when SRH 2D actually uses that mesh geometry, averages your cell or your mesh node elevations to get your cell elevation. And what that means is when you have that, if you don't have enough elements across, the top of your structure, it's going to miss that peak. And I know that's, Scott's talked about that in the webinars as well. So, point of that is, even by adding that much mesh resolution, you don't pick up a whole lot more information in the elevations themselves. Now the hydraulics can be calculated in a lot more detail. And so you're going to resolve a better velocity field with that many more mesh elements. So then if we kind of look at the results here, we'll start with flow distribution. And we had some ADCP data from the Corps of Engineers at 44,000 CFS, so a real low flow on the Mississippi. And so we've got kind of two transects there. We've got upstream of our bridge and downstream of the bridge near the entrance to Beaver Slough. So if we look at the table at the top left, we'll see that the measured flows in the main channel are about 36,300 CFS, and in the what I'm calling the refuge slough, it's near a wildlife refuge there, it's about 7,300 CFS. And you look at all the different ways that we looked at 4 different mesh resolutions, looked at using weirs to represent the wing dams, and actually adjusting the elevations of the mesh to make sure that the wing dams were captured with one element. None of those really made much of a difference on the flow split. One thing that did make a difference was we got some additional multi-beam data that was collected downstream of the bridge that we didn't have for those kind of those top 4 model runs. So that did have some effect, but overall not a whole lot. At the entrance to Beaver Slough, there was really no variation. And I would have expected some difference there because that's the location of the closing dam that closes off about half of the channel, but that did not have much of an effect on flow distribution. So then I looked at water surface profiles through the length of the pool. So this first slide is at 44,000 CFS again, and this is comparing the coarse and detailed meshes with the coarse and detailed meshes using the old terrain data. And we've got a few locations called out there, the entrance to Beaver Slough, where the wing dams begin in the reach and where the wing dams end in the reach. And not much difference in water surface elevation, I would say, for this much of a reach, 0.05 of a foot maximum between them. And between the coarse and detailed mesh, there was virtually no change. So that's just due to the bathymetry differences. So I also looked at incorporating the elevations of the crest of the wing dams into the model, and that had a little more of an effect. Could see about 0.09 of a foot at the upstream end. And then when I added in SRH2D, looks like the dashed lines unfortunately are not showing up here, but the top green line is SRH2D with adjusting the crest elevations of the wing dams. And so SRH2D is showing a little more energy loss than 2-flow FV was, but overall, similar conclusions. It's also important to keep in mind how low of a flow this is. It's much less than even the 2-year flow, and you most likely would not look at a flow this low for, unless you're looking at more sediment-related issues. We'll just kind of go through these quickly here. For the 2-year event, again, comparing the coarse and detailed meshes and then adding in an adjustment to the crest elevations. Not much of a change, 0.04 of a foot, 0.03 of a foot for the 50-year. Same thing for 100, 400ths of a foot for the 500 year. Finally, I wanted to show the velocity field differences. And this is, again, because we're looking at bigger picture, I looked at the difference in velocity magnitude, not necessarily how recirculation areas were captured between the different options. So using 2 flow FE at 44,000 CFS, you can see, so the plot on the left shows what happens if you add a more detailed mesh at the wing dam locations. Anything we see in red is where velocity actually increased, and blue is a decrease. So a lot of these changes that are showing up are 0.2 to 0.5 feet per second. If we look at the detailed mesh where you adjust the elevations of the wing dams and compare that to a detailed mesh, so again, you're taking more time to develop that mesh because you have to spend more time capturing that crest. Then we start to see a little more difference in that low velocity area along the bank. I should also point out that you could see, so our actual, this is the bridge that we were interested in. And so this is the most upstream, or the closest wing dam to the project. You could see no effect in the velocity at our actual bridge of interest. You could see down at the entrance to Beaver Slough, so even though there was not much of a flow distribution difference, there is a difference in velocity. So I didn't look at local water surface elevations there, but I would guess that there's probably a difference there then due to the velocity change. If we use SRH2D, you see similar changes in the velocity field. Little more pronounced effect when you hard code in those elevations of the wing dam crests. So as we go up through the remaining flow rates, I started to see some surprising results in the velocity field, actually. So as you refine the mesh, you see actually higher velocities in the kind of the wing dam field there. And I was pretty surprised to see that, actually. And the only thing I can attribute that to is really more of a mesh sensitivity in those areas, because it's kind of counterintuitive. You would think you add more detail, you're going to be picking up more of those high elevations, and you'd start to see some velocity wakes downstream of the wing dams. So again, going through the 50-year, kind of same trends, 100-year and 500-year. So to kind of wrap it up then, I would say the river training structures in this case did not have significant effects on the flow distribution in the area of interest. Local velocity field was impacted, minimal impacts on water surface elevation, and that's all relative. In this case, I would consider those changes minimal. If you have, some river training structures downstream of your bridge, and it's lower low chords, closer to the water surface, you're starting to not have as much freeboard there. That could start to become more important. In this case, it makes more sense to spend time refining the mesh around your bridge, not the river training structures. Include them if the velocity field extends to the bridge. It's kind of, without testing that, right, it's hard to know what that is, how far that velocity field difference could extend. So it kind of, depends on your velocities, fruit numbers, and so on. Also, collect multi-beam bathymetry data if the budget allows. I was surprised how much of an effect that it did have in this area. And then, another thing, keep in mind that even on a large river like the Mississippi, the velocity field throughout the reach can be sensitive to the mesh resolution. So with that, I'll take any questions.
Brice, any questions for Brice?
So thank you. Did you all, you looked like you all had a fair amount of ADCP data available to you.
Mm-hmm.
Did you all do a comparison of the velocity fields that you got from the ADCP data to your various model simulations?
Yeah, so we did do that. The points, individual points varied. On an average, if you look at a transect, on an average we were, within like a half a foot per second. And there wasn't a skew either up or down. Actually, and then if you look at all of the entire model, we were down like within, 0.2 feet per second. So we didn't go into a lot of detail to identify individual points and how those differences changed, what the differences were. I do think that because it is such a low flow, that a lot of the differences we were seeing were due to the bathymetry data, though, more so than an end value difference. So.
Thanks. Any others?
Regarding the mesh sensitivity, did you find a sweet spot where the velocities didn't change? Now, did you go like lower or higher in resolution, and then you found that if you go lesser in resolution, you'll get a similar answer?
Yeah, there would definitely be a point where that convergence would occur. We didn't go that far because the reason we extended the model that far upstream was to determine water surface elevation impacts. So we didn't care a whole lot about the velocity field. And as you could see, the water surface elevation wasn't sensitive to that. So yeah, I definitely know what you're saying. You'd see a convergence there.
Possibly one more.
This is nothing to do with your model, but for this ignorant person from the Northeast, what are these wing dams?
Okay. Yeah, I took that slide out due to time concerns, but I'll show it now. This is a kind of an extreme example of that, I would say. This is on the Missouri River near Indian Cave State Park. So on the upper left, you can see the natural state of the river, and then the lower left, they added a dike field, and these are actually pile dikes, so they're like wood posts that are driven down, and their water can flow through them. A lot of the wing dams that I was talking about in the upper Mississippi River are basically rock piles that were placed there to scour out the channel, and they were constructed really when the 6-foot channel was authorized before they built the lock and dam system. And from what I understand, they're not really as useful as they are, as they were for the 6-foot channel. So the Corps is not really maintaining them. But anyway, to follow through, you could see on the upper right, after just 2 years, you could see how much sedimentation occurred there. And then 12 years after original installation, it was completely vegetated with trees. So that illustrates the effect that they have in an extreme example.
All right. Thanks a lot, Brice.